welcome back to physics. The next lecture in our video lecture series is about torque. We'll learn a few things about torque today and how to apply it to our everyday life. So force is the action that creates changes in linear motion. We already learned that. So an object in motion stays in motion at constant velocity unless acted on by an unbalanced force. Newton's first law. For rotational motion, the same force can cause different results. And that force is called torque. So torque is an action that causes objects to rotate. So if you've ever turned on the water faucet at your house, it required torque to do so, and it causes that handle to rotate one way or the other, to either turn on the water or turn off the water. A torque is required to rotate an object just as a force is required to move an object in a line. So if an object is moving in a straight line, to change it, a force is required to change it. Same with torque. To rotate an object one way or the other, torque is required. So here's a couple examples of torque. It's called rotation, or torque is translational rotation. So translation is the ball moves in a straight line. Rotation is it rotates around as it moves. So this is translation and rotation at the same time. It's kind of what happens with torque, and we'll talk about that. So torque is created by force, but it also depends on where the force is applied and the point at which the object moves or rotates. So the object rotates at a certain point. We call that the center of rotation. So for example, you have a door. A door pushed at its handle will turn easily and open. But if you push that same door right next to the hinges, it is a lot harder to open. You can get up and go try it now if you would like. Or you can try it after you watch this video. Go to your bedroom door. If it opens inward, go outside and not close it all the way, but push right at where the doorknob is. It opens rather easily. Now close it and push with that same amount of force at the hinges and see how easy it is to open. So the distance affects the amount of torque that is applied. So the center of rotation is the point or line about which an object turns is its center of rotation. So just like if you turn a nut or something with a wrench, that center of rotation is right there in the middle. Same thing with the door, its center of rotation is at the hinges. So a door rotates at the hinges, and different things rotate based on how they're made in different spots. So a force applied far from the center of rotation produces a greater torque, and that's important to us, than a force applied close to the center of rotation. So if you've ever tried to change your tire, if you grab the tire iron right next to the lug nut, it gets real difficult to break that lug nut loose. But if you go down there to the very end of your tire iron and apply your force, it's much easier to loosen it up. The line of action. So torque is created when the line of action of a force does not pass through the center of rotation. So basically the line of action is where you're pushing it from. As long as it does not pass through the center of rotation, torque is created. So here's our center of rotation. As you can see on the nut, it's right there, and our line of action is where the hand is pushing, and we want that to be parallel to our center of rotation. And the farther away it is, the more torque we will produce. So the force applied must be perpendicular. So the lever arm is the perpendicular distance between the line of action and the center of rotation, annotated by the R there in our diagram. And you can see the person is pulling at a 90-degree angle to that line of action. So that's the optimal angle to get the best torque that we can get. So look at the diagram, you get the center rotation, you can see it annotated there on the left. The line of action is there on the right where the hand is pulling down, and the lever arm is the perpendicular distance between them. So to calculate torque created by force is equal to the lever arm, annotated by R, times the magnitude of the force, F. We've already talked about force. It is still measured in newtons, and the lever arm is going to be measured in meters. So here's our equation. Torque equals lever arm times the force. So torques can be added or subtracted depending on what they're doing. So if the torque acts on the object and they're combined, we can determine the net torque. So if more than one torque acts on the object, the torques are combined to determine the net torque. So if the torque tends to make the object spin in the same direction, it doesn't matter which, they are added together. But if the torque tends to make the object spin in opposite directions, the torques are subtracted. So if they're working together to help each other, we add them. If they're working against each other, we subtract them. So here's an example of adding the torques. You can see torque A on the left is 10 newtons down, and its lever arm is 0.2 meters away from the center of rotation. And B is also pushing down with 10 newtons, and its lever arm is 0.1 meters. So based on the fact that they're both pointing down, they're working against each other, not to help each other. So in this case, you'd get a plus 2 newton meters because we started with A. You could have started with B, and it would still work out to be the same. And then torque B, closer, is, we calculate it's negative 1 newton meters. So if you add them together, then you get plus 1 newton meters. So A is where we started. We got 2 newton meters of torque going down. And then B, we have 2 meters of torque also going down. So it becomes negative, and we subtract them. So we end up with 1 newton meter of torque. If B had been pushing upward, then we would have added them, and we would have gotten 3 newton meters of torque because they would have been working together to produce a net torque. The units of torque, kind of alluded to it before, are force times distance, or newton meters, because the units of force are newtons and the units of distance, or lever arm, are newton meters. So a torque of 1 newton meter is created by a force of 1 newton acting with the lever arm of 1 meter. So here's an example. A force of 50 newtons is applied to a wrench that is 30 centimeters long. Notice that our lever arm is in centimeters. So we're going to write down our givens. Here's the problem. Calculate the torque if the force is applied perpendicular to the wrench, so the lever arm is 30 centimeters. Our givens, our force is 50 newtons. Our lever arm is 30 centimeters, or 0.3 meters. What do we want to know? We want to know the torque. What's our equation? Torque is equal to force times lever arm. Sometimes you might see that R as a D. It's still the same thing. It's the distance. So F times D or F times R, either is acceptable. So we substitute in our information. Torque is equal to 50 newtons times 0.30 meters. And if we plug that in our calculator, we get a torque of 15 newton meters. So torque is fairly easy to calculate. We just got to figure out our force is always going to be in newtons, and our lever arm is either going to be in centimeters or meters. Just remember, if it's in centimeters, we have to convert it to meters. Here's another example, kind of a little bit different. We'll kind of talk about it. A boy and his cat sit on a seesaw. The cat has a mass of 4 kilograms and sits 2 meters away from the center of rotation. If the boy has a mass of 50 kilograms, where should he sit so that the seesaw will be balanced? So basically, the torque of the cat has to equal the torque of the boy for the seesaw to be balanced. So we're going to put all this stuff in. So you're always going to have to find the boy's lever arm is what you're looking for. And so we got both masses and the cat's lever arm. So torque is equal to the lever arm times the force, or force times the lever arm. And we know the force, or the weight of the boy, because we know weight is a force, is mass times gravity. Same for the cat. So the net torque has to be equal to 0. So we're going to solve for the cat. The torque of the cat is equal to 2 meters times 4 kilograms times 9.8 newtons per kilogram. That's not correct. It's 9.8 meters per second squared. So you work all that out, which would, I guess, be a newton kilogram, but we don't talk like that, so I got to watch what I borrow from people. So we end up with plus 0.78 or plus 78.4 newton meters. For the boy, we have torque is equal to, we don't know the lever arm, annotated by the D. I told you distance was acceptable, times his 50 kilograms times 9.8 meters per second squared. So now we need to solve, and we end up with negative 490 times displacement, or lever arm. So then we plug all that in. To find the net torque, they have to be equal to 0. So we have 78.4 minus 490 times the lever arm is equal to 0. So then we're going to have to move that 490 times displacement to the other side by adding it to both sides. And that gives us 78.4 equals 490 times the lever arm. And then we're going to divide both sides by the 490. So we get 78.4 divided by 490 and gives us a lever arm of 0.16 meters. So the buoy must sit pretty close to the center for it to be balanced, because the cat, its distance increases the amount of torque applied. Alright, so force and lever arm are not always perpendicular. We're not going to have to calculate this anywhere in this course, but I wanted to give this information to you for those of you that are going to pass on and go on to college. So when the force and lever arm are not perpendicular, an extra step is required to calculate the length. So it's in here in these notes you can see. You have to calculate the angle from perpendicular, or the line of action. So in this case it was 30 degrees. So to find the torque, you're going to have force times lever arm times the cosine of that angle from the line of action. In this case it happened to be 30 degrees. It could be farther than that. And then you plug that in and that will give you the torque. So that's all we need to know about this. This last part is just for your information. It's not something we'll have to do on the test or anything like that in this class, but I want you to understand it. All right, thanks and have a great evening.